everyone. Physics in the Flesh is back with the fourth Law of Universal Gravitation problem. Four 9.5 kilogram spheres are located at the corners of a square with side length 0.60 meters. Calculate the magnitude and direction of the total gravitational force exerted on one sphere by the other three. So here we go. First thing I'm going to do is draw a picture essential for a problem like this. So I've got four identical masses, which I'm going to call lowercase m, and they're arranged in a square. So I'm just going to draw that out. Now what I need to do is calculate the magnitude and direction of the total gravitational force exerted on one sphere by the other three. It really doesn't matter which sphere you choose. They're all going to feel the same force of gravity by three other identical spheres. So I'm just going to go ahead and choose this one right here. It's in the bottom left corner. Okay, so one more thing I forgot to add to the picture is the distance. We're going to call the distance between the masses d, and we're actually given the value of d in the problem. It's 0.6 meters. So focusing on this one mass, we've got an attractive force toward this mass, that one, and this one right here. Okay, so we'll call the attractive force to the one above it F up. We'll call the attractive force to the one to the right F right. And there's one more attractive force going on an angle. Okay, we'll call that F diagonal. Now, hopefully you see this from the picture. The angle between F diagonal and F right, or F diagonal and F up, that's 45 degrees because this is a square. Okay, so hopefully you see that angle there. All right, so what I need to do, because there's forces going in different directions, I'm gonna find the total force by finding the total in the x direction, which is gonna have a component from F diagonal, the total in the y direction, which is also gonna have an F diagonal component, and vectorly add them together. Okay, so in my x direction, Fx, I've got F right plus the diagonal force that has a component in the x direction. So if you take F diagonal and you multiply it by the cosine of the angle, so adjacent of theta, we get the x component. Now, we know that the force of gravity expression, Fg, is equal to gmm over r squared, the mass of one object, the mass of the other. In this case, both masses that we're considering one at a time, capital M and lowercase m, they're the same. So I'm just going to simplify this as gm squared over r squared. And that's what I'm going to plug in over here for F right. M and m makes m squared. So g m squared over d squared, because my distance between the masses is d, plus F diagonal, it's still going to be gm squared. Now don't write d squared because the distance between these two is not d. D is this vertical distance and the horizontal because it's a square. The diagonal is not d, however. Okay, this is how you find out the diagonal. Imagine this right angle triangle here. In fact, I'm going to actually flip it. Let's look at this one right here. Okay, if you have that right angle triangle where your angle is 45 degrees, your side length here is d, side length there is d. Okay, how do you find the side length of the final side? Okay, this is a special triangle hopefully you learned in math class. You've got the right angle triangle with side lengths of 1, 45 degree angles inside. Therefore, the hypotenuse is root 2. Okay, so in this case, the hypotenuse of this triangle is going to be root 2d. Okay, because it's root 2 times whatever equal side lengths you have on the other parts. Okay, so the distance is not d, rather it's root 2d, and then that whole thing gets squared. Now, cosine of theta, again, you could just plug it in your calculator, cos 45, or you could see from the diagram, cosine of this angle is 1 over root 2. Okay, that's another property of the special triangles, 1 over root 2. So here we go. Now I'm going to expand this, the root 2d squared. Root 2 squared becomes 2, d squared is d. So with that 2 in the denominator, I'm going to bring forward the 1 over root 2, bring that entire thing to the front. So leaving gm squared over d squared plus 1 over 2 root 2 gm squared over d squared. So now we've got the same expression here and here. So you probably guessed it, I'm going to factor that out. So gm squared over d squared, factor 1 plus 1 over 2 root 2. Okay, so yeah, it looks a little messy, but you know what? That's the expression for our attraction in the x direction, the gravitational attraction. So you could go ahead and do the same thing for y, or you could be really efficient and realize from the problem, because it's a square, because all the masses are the same, there's a lot of symmetry. And due to symmetry, it's the same force in the y direction as it is in the x direction. So due to symmetry, Fx equals Fy. Okay, that's going to simplify your problem a whole bit. So now that we have Fy as well, it's the same as this, so we can just say equals Fy. We're going to look for the total force by adding Fx and Fy together. Okay, so the total, Ft, if you want to write it as a vector expression, is equal to Fx plus Fy. Okay. So to find the magnitude, that's our first part. We're going to do Ft, use Pythagorean theorem, right? Because your x component, Fx, and your y component, Fy, are the two sides of the right angle triangle whose hypotenuse is Ft. So there you go. So Ft is equal to the square root of Fx squared plus Fy squared. Now, we just said they're the same thing, so technically you could just say Fx squared plus Fx squared, which is 2Fx squared. So square root 2Fx squared. And at this point, I'm going to plug in the expression I just derived for Fx in the blue. So square root 2 bracket gm squared over d squared. And that entire thing gets squared times 1 plus 1 over 2 root 2. That also gets squared. Okay? Right, because it's Fx squared. So everything Fx related has to get squared. Now, if you're going to take the square root of 3 products, okay, the square root of 2 is just root 2. The square root of something squared just undoes the squares, okay? So you're going to be left with root 2 gm squared over d squared, 1 plus 1 over 2 root 2. Okay, so at this point, I want to take this root 2 and multiply it through this term. Because it's multiplication, it doesn't matter which term you multiply it through, it comes out to be the same. So I'm going to take that root 2 and multiply it to this term right here, hence the two expressions inside. So root 2 times 1 is root 2. If you multiply root 2 to that second part here, it cancels out with the root 2 down here, leaving you with 1 over 2. So when you simplify this, you get gm squared over d squared, in brackets, root 2 plus 1 over 2. Okay, so this is getting a bit long, but you know what? It's actually not too bad. It's actually pretty simplified. So at this point, I'm just going to plug in my values and crank this thing out, figure out what it's equal to. Okay, so my g is 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. My mass, which I'm also going to square, is 9.5 kilograms. D is 0.60 meters, that gets squared, times root 2 plus 1 over 2. So just be careful when you're entering it in your calculator. It would be a shame if you went and did all this work and then just entered it wrong in your calculator. Okay, so there you go. Plug that in. You should be getting 3.2 times 10 to the minus 8 newtons. There's your total force. The magnitude. Now we have to find the direction. Direction's really simple. Remember, it's a symmetrical problem. Same force, same pull on the x and the y, right? We said Fx and Fy are the same, so you can just call Fy Fx. Hence, these two side lengths are the same, making this angle 45 degrees. Okay, so hopefully that's clear to you. Okay, so therefore, we can say that the total force is equal to 3.2 times 10 to the minus 8 newtons, bracket 45 degrees from positive x. Okay, because this is the x direction, 45 degrees above it would be above the positive x. And there you have it, guys. So please click that like button if you liked the video so I know that you learned something from it, and subscribe to Physics in the Flesh so you never miss a video from me. Stay tuned tomorrow at 12 noon for video number 91, Satellites and Weightlessness, Part 1.